We're going to look at solution to the heat equation of this particular scenario, satisfying that given initial condition. Let's see what we have here. So consider the conduction of heat in a rod 40 centimeter in length. So that is our length, big L, whose ends are maintained at 0 degrees Celsius for all t bigger than 0. Find an expression for the temperature distribution. So we want U of x comma t if the initial temperature distribution is given by this function. That is our length of the rod. So imagine you have a rod right here. So I can't really draw one. Let's just suppose that we're going to hold this end at 0. So that will be U of 0 comma t. That is going to be 0. This end is also held at 0. So this will be U comma 40 comma U of 40 comma t. That is also held at 0. So the length of this rod is 40 centimeter. Okay, so those are the boundary conditions. So these are boundary conditions. So now we know the up to the boundary condition, the solution to the heat equation is going to be U of x comma t is equal to the sum from n equals 1 to infinity of some constant bn times sine of n pi x over L times e to the power of negative alpha square n square pi square over L square times t. So that is the solution satisfying the boundary conditions are held at 0. Okay. Now we're going to substitute our L value here and here. So that means our solution would look satisfying the boundary condition as follows. The sum from 1 to infinity of some constant bn times sine of n pi x over 40, called L is 40, times e to the power of, now where is alpha squared? So we're given alpha squared right here in the problem. It is 1, and we know L is 40 because that's the length of the rod. So I'm going to substitute L is 40, as you saw. So this will give us e to the power of negative n squared, pi squared over 40 squared. That's going to be 1600 times t. All right, so this is going to satisfy boundary conditions held at 0, 0. Now we're going to satisfy the initial condition by simply applying the initial condition. So here our initial condition is right here. So we know that is that function. So now let's apply the initial condition, which is U of x comma 0, t is 0 is going to be this function. So we'll substitute this in here. So we will have the sum starting from 1 to infinity of some bn times sine of n pi x over 40. When you plug in 0 for t, this will be 0. So you'll have e to the 0, that's 1. So that's why we don't have that exponential term. And we're going to set this to our initial function, which is x. So what that means is you want to express this as a Fourier sine series. That's what that is, in case you're wondering what this is going to go next. So our function x, we're going to represent this. So here you're going to represent as Fourier sine series. So we know that Bn is going to be determined by simply doing 1 over L, the integral from negative L to L of that function f of x is x here, from negative L to L sine of n pi x over L is 40. Now, of course, you could put here 40 and negative 40. So we could do that. And here we're also going to substitute 40 as well. Now, since x is going to be extended as an odd function, sine is an odd function, you can simplify this integral a little better by using the property. You can double the integral. So this is 2 over 40, the integral from 0 to 40. So you go from 0 to L of the function x times sine of n pi x over 40 dx. Now, if you are curious where we're getting all of this from, you might want to look up a differential equation textbook and see how this happens to be the solution to the heat equation satisfying the boundary condition. So I'll leave that info out for you to discover. So let's carry on with the integration, and then we have our Bn for the solution. Once we have that, we'll just simply plug it in right here. So we're trying to discover what Bn is, satisfying this initial condition. Okay, so this integration will go by parts. Now I'm going to show you a quick tabular method to integrate this, but this is going to be done integration by parts. So please look that up if you think you are struggling with that concept. I will show you integration by parts in a shortcut, which is called the tabular method. So you create two columns like this. One column you're going to differentiate, and the other column you're going to integrate with respect to x. So that's how I like to write it down. So I'm going to differentiate this function, and I'm going to integrate this function. All right, so we'll put x right here, and sine of n pi x over 40 right here. All right, so differentiate x1 respect to x, you get 1. Differentiate 1 respect to x, you get 0. Once you get to 0, you stop. And now we're going to integrate until we reach this level right here. You'll see why. So integrate sine once, you will have negative cosine. We'll adjust the input. So you'll have negative cosine of n pi x over 40 divided by n pi over 40, which is the same thing as multiplying it by 40 over n pi. Okay, so a little use substitution as we're doing the integration. All right, then the next, we're going to integrate one more time. If I integrate this, I get negative sine of n pi x over 40 divided by n pi over 40, which is the same thing as multiplying by 40 over n pi, which will multiply to this constant term we have. So that will be 40 times 40, that's 1600 over n squared pi squared. All right, so now you're going to take this function, multiply it with this function right here with a positive 1. Then you're going to take this function, multiply with this function with a minus 1. And then the reason we stopped at 0, because 0 times whatever that was, it will be 0. So that's why you stop at 0. All right, so the result of this integration will be as follows. So make this a bit smaller so we have a little bit more room to write. Okay, all right, so hold on to that. So this integration will result in x times that function. So we'll have 2 over 40. I can also simplify that. That's 1 over 20. So we got 1 over 20. All right, now the integration. So we have x times this function right here. So it'll be negative, let me write it this way. We got negative 40x over n pi times cosine of n pi x over 40. Evaluate this from 0 to 40. And then we got minus, so the next function is positive. We'll have positive 1 times sine of n pi x over 40. And we're going to multiply this with 1600 over n squared pi squared. Evaluate this from 0 to 40. All right, so that's what it looks like. So now let's plug in the upper limit of integration into these x. So for the first piece, we're going to get, we got 1 over 20 times all of that. So 40 times 40, that's negative 1600 over n pi. And then we got cosine of n pi 40 over 40. So the 40s will cancel out. So this will simply be cosine of n pi minus from the lower limit of integration, and this minus, or rather this minus, that'll make it a plus 40 times 0 and whatever, right? So you know this is going to be 0. So the lower limit will give us 0. And then for the second piece, this one, when you plug in 40 into this x, you will have sine of n pi. Sine of n pi, sine of every integer multiple of pi is always 0. And then when you plug in the lower limit, you will also get 0. So this will completely go to 0. All right, so this is what we're left with. Little simplification. Then you should also know that cosine of n pi alternates between 1 and negative 1, which means you can also re-represent this as negative 1 to the n. Because if n is 1, you get negative 1. If n is 2, you get positive 1, and so on. So you alternate between those two numbers. So our coefficient Bn is simply 1 over 20 times negative 1600 times negative 1 to the n. over n pi. Now here I can use some laws of exponents. Here, -1, -1. That will be -1 to the n plus n1 power. So you'll have 1 over 20 times 1600 times -1 to the n plus 1 over n pi. And then 16 over 20, that will simplify to 80 over n pi times -1 to the power of n plus 1. That is your Bn for every integer value of n. All right, now we can substitute this into, so we're going to sub this in to our solution right there. So I'll go ahead and copy this for you downstairs. So our solution satisfying both initial and boundary condition. So we'll put this right here. This is going to be the following. So you'll have your Bn value, which is 80 over n pi times -1 to the power of n plus 1, sine of that, and exponential to that power. So you could stop right here. This is a good way to represent our solution. Or if you want to be super fancy, you can pull out 80 and pi outside of the summation because the summation belongs to n. So you could also play around with it and just be very fancy with your answer. So your solution to this heat conduction problem will be 80 over pi times the sum from 1 to infinity of -1 to the power of n plus 1 over n. And then you rewrite the rest. So I'll just go ahead and copy this for you. So saving myself some time. There you go. So this is our solution satisfying the initial condition. All right, I hope this helped you understand how to solve heat equation problems when both ends of the rod are held at 0. I do encourage that you look into the derivation of the solution. I'm pretty sure you'll enjoy that as well. Okay, I will see you next time. Take care, everyone.